anything. So what I'm going to do today is uniform accelerated motion. I'm going to start with just some introduction. I'm going to spend a few minutes introducing the topic. I'm going to try and give you a kind of a crash course in the first couple of slides, like kind of everything that you need to know, and then we'll get straight into questions. So I have some warm-up questions which are from the book, and then we can get into some exam questions. What I'll say is that this topic is actually quite challenging as an introduction, as the first topic. It's the kind of the first big topic that you come across in applied maths. It is a bit challenging. There's kind of a lot to it. So just bear with it. After this, I think what you get from this is you learn a lot about how you approach these questions, right? So there'll be something, you know, for every kind of question that you do, there'll be something to be taken from this approach here. Okay, so let's just go back to junior cert just for a moment and talk about this thing. When I did it, they call it Dad's silly triangle. Sorry. What's happening here? Not got used to the... Is this different today for some reason? Okay. So this here was like, the equation was distance was equal to speed multiplied by time, or speed is equal to distance over time, like meters per second and so on, okay? So if you had like, I don't know, if you have a particle that goes, maybe a car or something that goes from here to here, you look at how far they are apart, that's going to be the distance. And then you look at how long it takes, and then you can calculate the speed by looking at the distance over the time, okay? Now, what's unrealistic? So this is unrealistic. And the reason why it's unrealistic is if you just think of the situation of being at a traffic light, well, actually at the beginning, your speed is 0, and then you speed up, and then you might go constant speed for a while, and then you slow down at the next sort of traffic light. So if you ever travel from 2 points from A to B, you know, you're not going the same speed the whole time, okay? And in reality, what happens is that, like, you'll know this obviously from having, taken a journey in a car, is that, like, let's think about this. I'm going to draw a velocity time graph, okay? So let's think, as time goes by, right? Your velocity, maybe it starts at 0, maybe you speed up, maybe you kind of slow down a bit, then you speed up a little bit more after you go past the slower driver, and then you have to brake suddenly when you come back. So the point what I'm trying to say here is that your speed is always going to be sort of fluctuating, right? It's always going to be going up and down. Now, in the Leaving Cert Applied Maths course, what we're going to do is we're going to talk about linear acceleration, okay? So our speed is going to change, but it's always going to change linearly, okay? So we're either going to, like, not speed up or slow down. That would mean having a flat line on a velocity time graph, or we're going to speed up linearly, right? Or slow down linearly, okay? And there's a few things that we can already say about this here, like, okay, so for example, here for this part of the journey, what I can do is I could, like, let's say this is my journey here. I could break this up into, let's call this now, and from now on, I'm going to say S for distance or for displacement, okay? So S is going to mean displacement. That's one big change from junior cert, is that S means speed. But we're not going to talk about speed anymore. We're going to talk about velocity. And our velocity, this will be our initial velocity will be U, initial velocity. Our final velocity will be V. Then our acceleration will be A. And time will be T. So every time you do these questions, you're going to write down, well, I've written it down, you're going to write down U, V, A, S, and T, basically, every single time. You have to fill them out, okay? Okay, so, and why it's velocity is that, like, when we do the applied maths course, what velocity is it's speed, but it's speed in a given direction. So it's a combination of speed with direction. It's not just like how fast you're going, it's what direction you're going in. So we're always going to talk about velocity in the course, but we'll come back to that later. Okay, so the first thing is that distance is going to be, like, if we think about the case, let's, if we think about the case where we have, like, constant speed and no acceleration, so our speed is not going up and it's not going down. If it's just constant, then actually, okay, what's the distance covered? So S is equal to that speed, which we could call U times the time T, which is the same as this side here is the time, because this is from the velocity time graph. And then the height here is u, like so, okay? And that's actually just the area of that square there, okay? And what I'm going to do now is I'm going to think about this journey, and I'm going to consider the three different stages to this journey. So this is like, this could be a story of starting off at a set of traffic lights, speeding up to a constant speed. So you speed up to a constant speed, you drive at that constant speed, but then you see the next set of traffic lights, so then you slow down again, okay? Sorry about, you know, this line here, this horizontal line here is it looks like a road. Here it's time, okay? So it's sort of similar, I guess. As in, like, you know, we're still speeding up in this distance, but we're speeding up in this time. Okay, so the distance here is made up, so the distance overall is made up of three different distances. The distance that I cover while I'm speeding up, the distance that I cover while I'm speeding, sort of slowing down, and then the distance that I cover while I'm going at constant speed. And I'm just going to work out each of them individually. So this one here is just speed by time, but it's also the area under the graph. And if I look at the area under the graph for this part of the journey here, well, this is the same as, let's say, let's call this now, I'm going to call this T2, and this T3, and this T1. So we're going to use lots of subscripts. So, and this is going to be U here. So this will be UT1, right? So, or UT2, sorry. Okay, so that part of the journey there is just the constant speed U multiplied by the time that we're going for T. Okay, and for this part of the journey here, to get the area under the graph, what I need to do is it's a right angle triangle, right? So it's a half the base by the perpendicular height. So it's a half times T2 times the perpendicular height, which is just U, or sorry, T1 there, isn't it? A half times T1 times U. And if you think about it, actually, this area here, instead of thinking about the particle that goes from 0 up to the speed of U, we could think about the average speed, which would be 0 plus U over 2. And we could consider that, instead of it, think about a car that's speeding up or whatever, we could just think that of a car that's going at a constant average speed between those two values. And that would be this times the T1 would then give us the area of that box there, okay? Which is the same, what I'm trying to say is that ends up being the same as that area there, okay? So that's why we can say that the S1 is equal to a half times U times T1. And then in the same way, this one here, S2, is equal to a half times U times T3, okay? So what I want you to take from this is we're going to draw velocity time graphs that summarize our journey, and we're just going to understand that the area underneath the graph is a way to get the distance that we cover. And in the case that we were talking about, like, let's say, you know, this is just to relate it to something on the maths course. If we have like a journey where it's not linear, you know, you don't do this on Leaving Cert, okay? So this is not really important. But if you were like, I just want to connect it to calculus and integration and differentiation from the maths course. So imagine if you had something where you didn't have linear acceleration. So you sped up and you sort of slowed down and you wobbled about a bit and then you stopped suddenly or something like that. If this was like, instead of straight lines, if this was your journey, then we would, let's say that's V and this is T. And let's say our velocity is described like this. You'd integrate it to get the area underneath the curve with respect to T, and then that would give you the distance, okay? You don't need to know this, but sometimes it can be helpful to kind of connect up some ideas basically, so you don't have to remember too much. And another thing is that we could also find dv dt, differentiate that, and that would give us the acceleration, okay? So it's a way that these quantities connect to like other things that you're studying on the maths course. So I just wanted to throw that in there, even though you're not really going to use it. Okay, so the next thing that we want to say is we have, and these are in the tables, I think, the equations of motion, which are really important. Where do I put them somewhere hidden? Let me just go here. So in your tables, in the back of it, you've got this sort of applied maths and physics section where you've got loads of the mechanics section, right? And here you have these equations of motion here. So these are your equations of motion. And what I'm going to do and what you should do when you do this question is just sort of like, you know, like basically sort of replicate them on your page. I'm just going to just add this here for a second. Okay. So when you do these questions, this is basically all you need, and velocity time graph. So this and velocity time graphs will give you everything that you need to answer these questions. Okay. So velocity time graph. So you're going to draw these sorts of shapes like this. And then you're going to work out the area underneath the curve and so on, right? And you're going to work out, this will be S1, this will be S2, this will be S3, and so on. Okay, and you're going to need, like, as I say, U, V, A, S, and T. Okay, so U is going to be equal to the initial velocity, so the velocity that you start with. V is going to be equal to the final velocity. A is going to be equal to the acceleration. S is going to be equal to the displacement, and then T is going to be equal to the time. Okay. Now let's. I think we should just spend a few minutes like deriving these, because you are asked sometimes to derive them. Let's start with this one here. So if we look at this here, like so what we understand here. So imagine this situation here. Oh yeah, no, before we do that, I think we should just get a quick idea of how to just think about acceleration. I'm just going to do this real fast. So imagine you had a set of traffic lights, and let's say you start off at 0, and then when the traffic light goes green, then you're traveling at 10 meters per second after 5 seconds. And your acceleration is like linear and uniform, right? What does that mean? It means that every second you're getting an even amount faster. So after 0 seconds, you're going 0 meters per second. After 2 seconds, you're going 2 meters per second, then 4 meters per second, then 6 meters per second, then 8 meters per second, and then 10 meters per second. Okay. So what that says, this is just after 1 second, after 2 seconds, after 3 seconds, after 4 seconds, after 5 seconds. So what it's telling us is that we're getting 2 meters per second faster every second. So if you see the meters per second divided by second, well, what happens is when you divide a fraction like this is meters per second squared, okay? Now, this is an important point. If you see this, it doesn't really, this is like a kind of a neat way to write a unit, right? Meters per second squared. But what confused me when I was doing Leavenscert is like, what is a square second? Like, what does this mean? This makes a lot more sense. Like this makes sense, like 2 meters per second faster every second, right? That's what acceleration is. It's the change. So you're getting 2 meters per second faster every second. And then it just happens that the units kind of collapse into something that we always meters per second squared, or sometimes they write it like this, okay? And the point about it is that doesn't necessarily mean anything to you where this would, okay? So like what I would encourage you to do is always sort of like, you know, don't necessarily just remember things. Just try to maybe kind of build them, kind of construct them, because you can kind of actually remember them and understand them a bit better then, right? Okay, so let's go back to this. I'm just going to finish off this sort of crash coursey part sort of section, and then we'll go into actual questions. What I want to do is derive those equations of motion one at a time. Okay, so the first one, let's say I'm accelerating from like this speed here, u, to this speed here, v, in a time that goes from 0 to t, so in t seconds. So there's my point there, and then I'm going up like this. Okay. Now, what am I thinking about for acceleration? Oh yeah, okay. That's why it's not working. So I just have to start this pen tablet thing. Right. Okay. Okay, so yeah, so that was, sorry about that. Okay, so okay, let me just say, okay, so what I want to do is I want to work out what the acceleration is going to be, right? So what the acceleration is going to be. Now, what I'm thinking about with acceleration, let's say if I went from 0 up to v in this time, I would say that my acceleration is faster. Or if I went from 0 up to, let me just do it with the line again. Like I could go from 0 to v like in this time, right? Then I would say my acceleration is slower. So what that's saying is that the acceleration is actually the slope here. It's actually m. It's the slope of that graph, okay? And what I'm going to do, you know, for m, so m is equal to y2 minus y1 over x2 minus x1. So I need 2 points. So let's just get 2 points. So this here is like the point 0 and u. So t is the x. So our point xy. The x value of this point here is 0, and then the y value is u, and then then it's t and v. Okay. So if I'm going to say y2 minus y1, it's v minus u. So v minus u over t minus 0. So a, which is what the acceleration, sorry, what the slope is we call that a here. That's why it's just the slope, but on the velocity time graph, we understand that the slope means acceleration because it means the change of velocity. Okay. So a is equal to v minus u over t, and now if I just simply multiply across, at is equal to v minus u, and I bring the u to the other side, so at, but I'm going to say it plus the u is equal to the v. In other words, v is equal to u plus at. Okay, so that's the first one. This one here. Okay, let's do the last one here. So how do we do the last one there? So if we now think about this again, exactly the same picture. Let's just work on the same graph because we'll just use a different color because it'll save a little bit of time. If we want to work out like what is that S there now? So what is that S there now? Okay, so we're going to try and use dst, right? So we know that that means that distance is equal to speed by time. So we're going to multiply like a speed by a time. But what we're going to do is we're going to take the average of those two, u plus v over 2. To get halfway in between there, and you see then it's going to be, it's going to be there, right? So the area of that area there. So this area here, let me just do it here in red. This area here underneath the red graph is the same as this area here underneath the green graph, right? Why? Because this little piece of a triangle that's missing is stuck here on top, okay? So this formula is then u plus v over 2. So that's what S is, okay? So that gives us the second formula. So now we have this one and we have this one. And now we need to get this one here. So what we want to show, I always say like want to show that S is equal to ut plus a half at squared. And the rule is that I'm not allowed to use this to prove this, okay? I'm not allowed this, that's kind of a little bit nuts if I was to prove, but I can use I can use anything else. Okay, so I can't use this one to prove this one, but I can use this one, and this one. And what I'm going to use is this one and this one, okay? So I'm going to use v is equal to u plus at, and I'm going to use S is equal to u plus v over 2 times t. Okay, so now how do I know which way to go about? Well, I have this little clue that I have S equals, so let me choose this one here, S is equal to. So I start there, S is equal to u plus v over 2 times t. But if I just write that, I haven't gotten anywhere. So I'm going to go back. I'm going to say u plus something over 2 times the t. And what I'm going to put in, instead of v going here, I'm going to put in that stuff. So u plus at. And then then S is equal to 2u plus at times t, and then still divided by 2, and that's going to be 2ut over 2 plus at squared over 2. In other words, ut plus a half at squared. Okay, just a quick note. We can also differentiate this with respect to t. The S dt is equal to, if we differentiate this with respect to t, the t will vanish and we're just left with the u. And then here, this will be a half a times 2t plus a half a times 2t, and that this will cancel. So this is u plus at again. What's the S dt? Well, the S dt is v. Okay, so this is how you can go from this one back to this one using calculus if you want. Or you can go from this one using integration to get to this. These are all fine methods, okay? It's just, I'm just sort of connecting some things up for you. Okay, and then the last one here is, I just need to get this derivation because I just forget it. So, seeing if I can kind of quickly see how they get it. Okay, so then I can just probably sub it in. So I don't think I'll do it the whole way out because I don't think you're ever asked this one here. But what we can do is we can write down, so we want to prove that v squared is equal to u squared plus 2as. And what we're going to do is we take v is equal to u plus at. And now I'm going to say v minus u over a to give me t. And now I'm going to take, I think, s. So this is what I want to show. Now I'm going to say s is equal to v squared, sorry, s is equal to the previous one that I had, ut plus a half at squared. And then it's going to be s is equal to u times v minus u over a times t plus a half a, and then v minus u over a all squared. And then when you work all of this out, you end up going a whole bunch of lines down. You end up getting to v squared is equal to u squared plus 2as. So there may be a different derivation. There's always going to be a few different ways. But the point about it is, if you want to, I don't think you have to. I think you might have to derive this one or this one, perhaps, in the exam. I don't think you have to do this one. But the point is, if you're looking for this one, you can use all of the others, right? You can use the others. Or if we're looking for this one, we can use these ones if we want, right? So, and also one that's not given here is a is equal to v minus u over t, which is the slope, the slope formula, which came from the slope formula. Okay. So having said that, we basically now have enough to start answering some questions. So what we're going to do is sorry, 1 second. Okay, so what I'm going to do, every question, I'm just going to have this up here in the corner, and then I'm going to decide. Essentially, what I'm going to do is I'm going to read this question, and below I'm going to write like usually u, v, a, s, and t, and then I'm going to write down what I have. And usually for the first types of questions anyway, what happens is that we're going to have like 3 of these things, and we'll be asked to find like a 4, right? Okay, and then what we have to do is, like, if we were given u, v, and s, and we were asked to find a, well, we need to find an equation over here which unites u, v, a, and s, and it's that one, okay? Or if we were given like u, v, and a, and we were asked for t, well, what's an equation that unites u, v, a, and t? It's that one, okay? So it's as simple as that when it comes to it. These questions get more tricky than this, but this is just to get started, okay? Okay, so a girl on a bicycle accelerates from 2 meters per second to 12 meters per second over 4 seconds. Calculate her acceleration and the distance covered. Okay, so straightforward one to begin. Accelerates from 2 meters per second. So the initial velocity is 2 meters per second. So we're going to call that 2. The final velocity is 12 meters per second, v, and she does that in 2 seconds. And I'm looking for a, which is this one, and I'm looking for distance, which is like this one, okay? So let's get like a first of all, okay? So for a, I've got u, I've got v, I've got a, and I've got s. So the equation that I need is like this one, because that's, so that I'll write that down. V squared is equal to u squared plus 2as. So this is just a warm-up. Probably this is like a lot of you are already like, you know, fine with this stuff. So I just want to do a little warm-up before we start. Sorry, and this is sorry, that was happening. Sorry, I wrote this down, didn't I? Sort of wrote it down too quickly. Let me go back. So this happened in 4 seconds. So this was 4, okay. And we were asked for a. I'm not too sure how I did that. So we're asked for a. So we need something that unites u, v, a, and t, and it's this one. So v is equal to u plus at. So that's 12 is equal to 2 plus a times 4. And if you have a look here, we have an equation, but we only have one unknown. And so we know that we can solve it. Okay, so I'm just going to get everything over to the other side. So 12 minus 2 is equal to 4a. That's 10 is equal to 4a. That means that a is equal to 10 over 4. 2.5. And I could just go ahead and stick down meters per second squared. So I'm not going to carry, like you see the way that meters per second, I didn't write it down. So what I want to do is ensure that all my units are in meters, seconds, kilograms, and so on. And that means that, like, okay, they're all good. So at the very end, we know that the answer that we can get out will be in SI units, right? So then we can just put in meters per second squared at the end, okay? And then the distance covered, then we're looking for the distance covered, right? So we're looking for S. And now we know that this is 2.5, so we actually have a choice. So we can go for, well, which one should we go for? I think we should maybe go for S is equal to UT plus a half AT squared. Maybe that one's easier. So that would be S is equal to U2 times 4 plus a half times A, which is like 2.5 times like 4 squared. And then we just work that out, okay? Again, that's an equation and it has one unknown, so we know that we can solve it, okay? If we had two unknowns in the same equation, then we would have to have, then we can't solve it, right? Not with one equation, we need a second equation, but we'll get into that. That'll come up later. Okay, so this is another one again. I don't think I'll do it all out. I'll just say U, V, A, S, and T. So you kind of do it as a form, okay? So every time you answer one of these questions, you're going to have like, you know, this, we'll just fill this out, right? So this time the car is slowing down from 40 meters per second to rest, in other words, to 0, in a distance of 100 meters. And we want to find the time taken. Sorry, wrote that down wrong. And we want to find the time taken. And we want to find and then this time it's deceleration. So whatever answer that we get out here, we know it's going to be a negative, okay? So we find the time taken first. So this is the first one that we're after. Let me just get this. Okay, and which one is it going to be? So the time taken is what we're after. We have U, V, and S. So what's that going to? So I'm going to say, and we're looking for T, right? So which one is that going to be? So A is equal to. So which one has U, V, and S and T? Is that this one here? Yeah. So S is equal to U plus V over 2 times T. So that's going to be 100 is equal to 0 plus 40 over 2 times T, which is like 100 is equal to 0 plus 40 over 2. That's going to be 40 over 2. That's going to be 20. So T is going to be equal to 5, okay? So I have that, that's now 5, and now I'm after A. And then it's like, okay, so A then would be, I'll just say V is equal to U plus AT. That's the easiest one to use. So that 0 is equal to 40 plus A times 5. So that's minus 40 is equal to 5A. So that's A is equal to minus 8, okay? So yeah, these are just warm-up questions to start with, but just to kind of get us into the system of like writing down U, V, A, S, and T, and then also having like these equations of motion and then just selecting the one that we want, okay? So then it says here, the distance that the car would take to stop, find the distance that it would take to stop if from 40 meters per second if its deceleration were doubled. Okay, so right now we're finding that the deceleration is like minus 8. So that would mean if the deceleration would double, it'd be minus 16. So it's just like now go back and what you'll notice with these questions is that there's going to be like these longer, wordier type of questions, and you're going to have to kind of do a kind of decipher what's going on and then fill out a form. So what I like to do is like look at the question, but then the moment that I can get away from the question where I'm no longer thinking about whatever it is, cars or bicycles or whatever they've talked about, you know, then as soon as I can get away from there, then the better, okay? So, okay, so that's just some warm-up questions. Any questions so far? Anything that is unclear? Or I know it's probably a little bit basic to start off with, but I'm going to get into an exam question, just trying to cover some of these basic kind of points first. Okay, so now we have to draw these velocity time graphs. So we can expect that the velocity time graphs are going to have like, so we're going to draw these velocity time graphs. Probably won't need this time. Okay, so these velocity time graphs, they're gonna you're gonna have a period of sort of acceleration, then a period of like no acceleration, and then a period of deceleration. Okay, it's not always going to be like that, but it's often going to be like that. Sometimes they just like accelerate and then they just decelerate, or sometimes they accelerate and then they just stay like at this. Okay, but what we have to do is like look at the picture, and we're going to have to basically like just make the graph from the picture. And what we're going to notice is that there's going to be like different stages to the journey, right? So let's say like stage 1, like stage 2, maybe stage 3, and we're going to sort of basically list all of these sort of separately, right? And we're going to write down for each of them like a UV, AS, and T, a UV, AS, and T, a UV, AS, and T. And what I'm going to do is like a little subscript for a 1 maybe. This is a bit overkill for this example, but you can kind of get used to this sort of stuff. You know, we basically in applied maths and physics, like we use up every single letter. And so we use lots of subscripts, right? Just to give us more, you know, so we can have multiple U's, right? And not get confused, okay? Okay, so a particle starts from rest. And let me sort of fill out down here. So we're in stage 1. A particle starts from rest. So U1 is equal to 0. And it moves in a straight line. So that means that's the linear part, right? The linear accelerated motion. Okay, so everything will always be in a straight line for these questions. In a straight line with an acceleration of 0.5 meters per second. And acceleration, so that's a plus. Deceleration would mean minus. And it does that for 8 seconds. Okay. It then decelerates uniformly to a speed of 3 meters per second in the next 4 seconds. So then it decelerates uniformly to a speed of 3 meters per second. So its final speed is then 3 meters per second. It does that for 4 seconds. And then it maintains this speed for another 5 seconds. So whatever that final speed was, so the final speed here was 3 meters per second, and it just maintains that speed. So U is equal to V. If it's maintaining its speed is not changing. So that means that the acceleration is just 0, okay? And then it does that. And then finally, okay, they've given us an extra stage, right? So I'll have a stage 4 now for the journey. A stage 4, U, V, A, S, and T, subscript 4, all these 4 subscripts, okay? And then then it decelerates to rest again, so its initial speed is whatever its final speed was in the last bit, which is 3, and it decelerates to rest at a deceleration of 2 meters per second. So this is an A. This is my A here. So this is -2, and that's all the information that we've been given. And now what they're saying is draw the velocity time graph for the journey. Okay, so let me just draw this here. Okay, and what I'm going to do is I'm just going to mark off these stages just sort of roughly, right? So that was 8 seconds. That's 8 seconds followed by sort of 4 seconds followed by sort of 5 seconds, and then I don't know how much this is going to be. I'll just put that there. Okay, and okay, so let's just read it off. Okay, and like I'll mention this bit now in a second. So okay, so we start here. And we go from here up to some speed, and we're going to call that speed there. We're going to call it V, okay? So we'll just call that speed V. Okay, so that's where it accelerates up to, okay? So I'll just draw that bit in. Okay, so then it immediately decelerates to a speed of like, let's say here, that's going to be 3. So it decelerates to a speed of 3 then, so that's here. Okay, then it stays at that constant speed for the next, whatever that is, 5 seconds. And then finally, then it decelerates, and it decelerates what's going to be like so. Okay, and what I'm going to do now is I'm just going to just add a little extra bit to the diagram here, like just going to do this like that to kind of clearly mark off the different phases of the journey. Okay, so first of all, this was 8 seconds. This is like 8 seconds. This is like 4 seconds. This is 5 seconds. And I'm going to call this t seconds. So the total time for the journey will be like 8 plus 4 plus 5 plus t. And then this, let's call this S1, S2. These are the distances that are traveled. So the total distance is going to be like S1 plus S2 plus S3 plus S4. Okay. Now, what else can we say? Oh yeah, the other thing that we can say here is that like this is a kind of a nice thing, right? So see this U1, V1 here, right? So actually V1, if you think about the end speed here, is the initial speed here. So U2 is equal to V1. And see this is V2, so U3 is equal to V2, which is just 3. And then you see this is V3, so U4 is equal to V3. So you can see there's a kind of a connection in between these different sections, okay? So that's going to be really crucial. You're not going to be given that. You have to know how to do that, okay? That's all you have to do from this question, just like make the velocity time graph. But this is very important to be able to do that, okay? So I have a proper tricky, I started to get into exam questions here. I'm just going to see what else I have. Oh yeah, so, and then it's sort of like, okay, so these were some of the things that you're then asked to do, which was basically kind of like what I covered from there. So the greatest velocity during the journey. Oh yeah, and then yeah, sorry. So from here, the greatest velocity that we reach during the journey is that velocity, right? Because we know we accelerate, then we decelerate, then we go at constant speed, then we decelerate. So that's the greatest velocity. So basically that question is like, just find V. Now we have, you know, U and we have A and we have T. So we can use the equations of motion. Just put them up there. We can use, we're looking for V, right? So we can just go ahead and use the top one, okay? For that. Then what's the next thing? It says find the total time for the journey. Well, again, the total time for the journey, well, we know what those three are. We just don't know what that last time there is. However, we do know this one, and this one. So then we can find this one and then we'll be able to sub it in, right? That's T there. So, so that's how we would find the total time for the journey, okay? Okay, so I'm just eager to move on. Is everyone okay with velocity time graphs, at least so far that I've presented it? If you have any questions, just you can also, okay, so mute yourself and say the question if you want. But or put it into the chat. So, okay, so okay, so this is so there's so what's going to happen is that sometimes we're not going to be given enough information. We're not going to be given enough information to kind of maybe come up with one of, we might have, our answer might like lead to like an equation instead of like the answer leading to like a number, like S is equal to 4 or T is equal to 5 or something like that. We might have one that leads to an equation as our answer, and we might have ones that lead to simultaneous equations, okay? But nonetheless, we just follow the same routine, okay? So we're going to use this the whole time. We're going to use a velocity time graph, and we're just going to work away as normal and see where we get. Okay, so a cyclist starts a 100-meter race. And I usually just sort of start writing things down. Starts the race at a speed of U is equal to 4 meters per second and accelerates to his maximum velocity of 16 meters per second. He continues at this speed for the rest of the race, and the total time for the race is 7 seconds. Okay, so this is kind of a lot to decipher, and what's going to really help me here is a velocity time graph. Okay, so let me just draw that down there. So this is my velocity time graph. Okay, so here is, what's that going to be? So that's going to be 4, which is when we start, and we get up to 16. Okay, and what do we know? So we know that the cyclist accelerates uniformly, okay, up to that speed there. And then the cyclist travels at constant speed for the rest of the race, okay? And then let's say that's the end of the race, right? Okay, so what do we know? Well, we know that the total time here is, the total time is equal to 7 seconds, okay? So what I'm going to do is I'm going to say that this is x seconds, and then that would make this 7 minus x seconds. And what's the other thing that we know? Well, we know the other thing that we know is that s is equal to like 100, right? Okay, and we know that this is 16. This is 16 here. Okay, so they say find the total time for the rate. Okay, so find the time spent accelerating, that's x, okay, that's the time spent accelerating, and then find the rate of acceleration. So then they'll find that value of a, okay? Okay, so basically the question is find x, and once we have x, you see, once we have, that'll be our time, right, for that first one, and we already have the u and the v for the first one, so the a will be, we can just use v is equal to u plus at to get what a is. So the question is really to get time, which in this case here, we're just calling x, okay? And you have to be kind of versatile with that. You have to be prepared to, you know, sometimes call it t, sometimes call it x, sometimes call it t1, and just not get confused by that. Okay, so what I'm going to say is that my s is made up of an s1 and an s2. Okay, so that's s1 plus s2. That's what my s is, and my total s is equal to 100. So let's just look at the, well, let's look at the s2 first of all, right? So the s2 is going to be this side times this side, okay? This side is 16, this side is 7 minus x. So it's 16 times 7, it's just the area underneath the curve, okay? So that's the great thing about the velocity time graph, that you can just look about the area underneath the curve to get the distance traveled. Okay, so this time here, well, we could, like, say, take this block here if we wanted to. So that would be 4x, right? That would be 4x. And then we could take this triangle here, which would be like, well, what's that height there? That's 4, sorry, that's 4 to 16. So that's 12. So then plus like a half the base, which is a half times x times the height, which is 12. So we can say that that's 4x plus 6x, so that's 10x. So we can work out what S1 is by looking at these two different pieces if we want to, or we can use that formula there. So that could be S2 is equal to u plus v, 4 plus 16, over 2 times the time, t, which is x, which is the same as 20 over 2 times x, which is 10x. Okay, so we get it in the same way, okay? So we have that, so that's S1. So we have that, S1 is equal to 10x, and S2 is equal to 16 times 7 minus x, and then that's equal to 100. And so when we look at this here, well, you see, we have an equation, and we only have one unknown in it, so we can solve it. So that's going to be 10 plus, okay, 7 times 16 is going to be, what's that, 100 and, what's that going to be, 112? Minus 16x is equal to 100, then I'll just bring the, sorry, that's 10x, isn't it? So that's minus 6x is equal to like minus 12, because that 100 comes over, 100 minus 112 is equal to 12. And that will give me, divide across by, that's x is equal to 2. So this takes 2 seconds, and this takes 5 seconds, right? So that's the questions where, like, so this is where we kind of ended up with, which was like different to the previous questions where we just got a number out, right? But it's using exactly the same steps. So we just have to trust in our ability, do everything exactly the same way. Don't deviate in any way, just do exactly the same stuff. And then, you know, maybe we get an equation out, and then we have to do a little extra at the end, okay? So it's just basically not like when you see like when something like that comes out, not like you want to be consistent, always doing the same thing, just keep your nerve, basically. Okay. And this is another one here. So, so this is like one that should lead to a simultaneous equation as the answer. So let's just have a look at this one and try to decipher it as we do it. So train covers. Just going to bring it up in case. So a train covers 24 meters in the first 2 seconds after it passes a signal post, right? So let's write down. So the train, let's say let's say there's going to be a part one of the journey, right? So for the first part of the journey, there's going to be an S1, which is 24, and there's going to be T1, which is equal to 2. And then it says, and it then covers 51 meters in the following 3 seconds. So then it's going to be like S2 is equal to like 51, and then T2 is equal to 3. And it says, assume that the train is accelerating uniformly. Find out how far it will go in the next 3 seconds. So let me just see how we're going to approach this. So yeah, that's one thing here. Okay, so let's just put this in here. Okay, so it says assume that the train is accelerating uniformly. So here we're talking about acceleration. Okay, it's kind of a hint. Okay, so this is like an acceleration. So what if I put down acceleration? You know, what's the acceleration here, right? And what's the acceleration here, sort of thing. And if I look over here and I find an equation that has S, T, and A in it, it's this one here. So why don't I don't know what the U1 is, right? Say that U1 is just equal to U. And I'm going to say A1 is just equal to A, because it's accelerating. The acceleration is, assume the train is accelerating uniformly for the entire time, right? So I'm just going to call that acceleration, sorry. I'm just going to call that acceleration A. Okay. And what I'm going to do here is I'm going to do something sort of sneaky. So, and this is like, may not seem, this is like, you always like, when you see like solutions to tricky applied maths questions, actually there's a stumbling block along the way. Let me show you what that stumbling block is. So let's say this is the journey, right? So in you know, the first part of the journey, like, is that 24 meters, right? And that takes like T is equal to 2. And then the next part of the journey measured from here to here, okay, is T is equal to 3. And what I can say is at the beginning, the U1 is equal to U. And then I can put that U1 equal to U there, and it's constant acceleration. So I know it's got the same acceleration in both the stages of the journey. Okay, so what's the sneaky thing? This is the sneaky thing here. What I'm going to do is adjust here. See, I'm not going to say this is T2 is equal to 3. I'm going to say T2 is equal to 5. So I'm going to consider this sort of second part of the journey to be the whole journey from here. So the first part, the first sort of part of it that I'm considering, this part, is I'm just looking at starting here and ending here and doing that in 2 seconds. The next part of it, I'm not going to think of it starting there. I'm going to think about it starting here and going all the way up here. Okay? And you'll see why in a second. So that would change my T2 to be 3. And then the distance, well, this is a 24, this is 51. So that distance now becomes 75. Now, why am I doing all of that? Why am I doing that? Because this is A2, this is a U2. I can say that U2 is equal to the same U as I had at the beginning. And now what I'm going to do is take that equation, apply it here, and take the same equation and apply it here, okay? So this one here then becomes, this first one becomes S, which is 24, is equal to UT, so that's U times 2, plus a half A times T squared times 4. And then the second one's going to be 75 is equal to U times 5 plus a half A times 5 squared, which is 25. Okay. Now, like, let's have a look at what I get from this. Let's go over here. Okay, so if I have a look at this here and just consider these 2 different equations, and I know you probably already know this, so this is equation 1, this is equation 2. If we look at the first equation, we have one unknown and a second unknown. And then the second equation, we've got one unknown and a second unknown, and the same unknowns. So this is a simultaneous equation. Okay, and then we're going to be able to cancel out one of the U's, and we'll be able to find both U and A. Okay, now this sort of thing that I did here is a little counterintuitive. It's like a trick, but once you know the trick, like basically the course is full of like standard questions plus tricks. And once you know the tricks, then you're going to be fine. Okay. So I want to move on because we've got 10 minutes left. So I want to get into some proper exam questions. In fact, I want to get to one proper exam question in particular. Okay, so the first one that we're going to talk about in the course, and it'll be the next thing that we cover. So in the first 3 lessons before Christmas, we're going to do like basically these linear acceleration problems. Then we move on to projectile questions where someone throws a particle to another, like a ball to another person, something like that. Okay, now this one here seems like it's going to be like a projectile question because someone's throwing a ball, but the difference is that they're throwing the ball vertically downwards, okay? So actually in practice, this question is no different from a car accelerating at a traffic light. It's just moving downwards instead of sideways, okay? So that means that we can use all the same formulas that we were using before. Sorry, not that. Okay, so the ball is thrown vertically downwards from the top of a building of height h. So S is equal to h. The ball passes, so let me just sort of draw this down now. I'm going to start drawing all the time, right? So this is the top of the building, this is the bottom of the building. And the height of the building is equal to h. From here down to the bottom, okay? Okay, the ball passes the halfway point, that's h over 2, when t is equal to 1.2 seconds. Okay, and then and then it takes another 0.8 seconds to finish off the journey at the bottom. Okay, so now what I'm going to do is consider 2 parts of the journey, from here to here and from here to here. For the first part of the journey, well, u is just, we don't know what it is. U is just u. V is, we don't know what V is. B is, we don't know. A is equal to G. Now it's not minus G because G here is just accelerating. Like if it was being thrown up and then it fell back down, then G would be working against the direction of motion. So it would be decelerating the particle, but here it's just accelerating the particle because it's thrown up. You're always choosing a direction to make positive, and here we just say downwards is going to be, this is just positive, okay? So A is equal to G, which is 9.8 meters per second squared, and then we have like S is equal to H over 2, and then T is equal to 1.2. And then for the second part of the journey, well, then U is equal to U again, V is equal to, we don't know, and then A again is equal to G. This time S is equal to the full height of the building, and then T is equal to the 1.2 and the 0.8, so T is equal to 2. And if we look at this here, actually we have the same problem as we had before. So the 2 unknowns, and I'm going to use S is equal to UT plus a half AT squared. And the 2 unknowns here are S and U, and then S and U, okay, for both of them. So I'll say H over 2 is equal to UT, so that's U times 1.2 plus a half times G times 1.2 squared. And then here H is equal to U times 2 times plus a half times G times 2 squared. Now, what we do now is we actually just solve this. So we have 2 equations, so equation 1 and equation 2. So we have 2 equations and we have 2 unknowns in the first, and we have 2 unknowns in the second, and they're the same unknowns, so we can solve this. And actually the simplest way to solve it is just to multiply this 2 by the first one, then I'll have H on the left-hand side because that will cancel off, and then I'll just take whatever I have here and sub it in for that H there, okay? So that's just like solving then the, so from wherever point that you start on, you want to just sort of like start drawing pictures, start writing down information until you get into familiar territory. And once you've done that, then it's just, I'm not going to do it. I'm like, you know, you don't always have to do every question right out to the end, because actually this is like 80% of the work here, right? To actually just set it up for yourself to be able to finish it off. And the question that I want to get to is this one here. And I don't think I'll have time to get to it. So I think I might just start there next time. Yeah, I think I'll start there next time. So this question here is one of these, this is like your typical Leaving Cert question that I'm working up to, right? And what they do is they describe a kind of a complicated story. Like we're told that Anya travels from her work to school every morning. On Monday, she does it in this time by doing this acceleration and stuff like this. On Tuesday, she does it in a different, and then we have to basically draw the two pictures out and then figure out how long it takes to get to the school and stuff. By now, something like this is a lot more involved, and it's very, very easy to make mistakes. And that's why this is hard, because it's sort of like lots of little bits that you can make mistake with. But nonetheless, we're going to approach it basically in the exact same way. We're always going to draw like a velocity time graph. And that's why I'm kind of spending so much time like kind of showing you these earlier questions, because even though these questions are easier, this is to say, this is the bread and butter. This is like what you need. And you need to kind of like sort of like get a question and break it down into smaller bits and pieces, and then answer those bits. And then when you're finished with those bits, then make an equation with what's left over, right? So it's sort of like, this is all of your answers will be made up of these steps, okay? So, okay. So this time we're gonna think about another problem with a vertex. So again, this seems like it could be a projectile question where something's being thrown up in the air and moving across in this parabola type of shape. But that's not what's happening. It's thrown vertically upwards and then it comes straight back down. So it's not different from like, I don't know, like it's not different from, let's say, for example, I'm trying to think of an example, like if you did like a bungee jump or something, you went down and then you went back up again or something like that. Like, okay, so it's, or if you were sort of driving, if you were running along with a bungee cord sort of attached to it, that slowed you down and sort of fired you back, right? So it just doesn't really matter that we're traveling kind of vertically, okay? Okay, so the ball is thrown vertically upwards, and then it turns around and it comes back down. And it's thrown vertically upwards with initial speed of 44.1. And it says we want to calculate the interval between the instants when the ball is 39.2 meters above the ground, okay? Okay, so we want to find when S is equal to 39.2. Okay, so the ball is thrown up from this point here in the ground, which we'll call 0, and it passes by a point S, which is 39.2, and it can pass that point on the way up, and it can pass that point on the way down, okay? And we want to find the time. This is what the question is about. The question is about time, okay? Okay, so what else do we have here? Well, we also know that A is equal to minus G. It's equal to minus G this time because it's the particles are thrown up. So this is upward. This is the direction that we consider positive now because it's the direction the ball was going. So that means gravity pointing down would make gravity a negative, okay? Okay, and if we look at this here, we have a U, we have an S, we have an A, we have a T. And so what's that going to tell me? So that's going to tell me, if I go back over here, that I want to use this equation here. S is equal to UT plus a half AT squared. So S is equal to UT plus a half, and then A, and then T squared. So that means that 39.2 is equal to U, which is 44.1, plus a half times, minus a half, isn't it? Minus a half times G. And you know what? G is 9.8. So a half of G is 4.9. You just get used to that 4.9, that 9.8. So I'm going to go back over here and say minus 4.9. And there was a T there, wasn't there? And then there was a T squared, okay? And we're just on time, so I'll just finish this off now. Okay, I'm going to bring everything over to the left-hand side. 4.9 T squared, right? I lose the minus, don't I? Okay, then I bring over the minus 44.1 times T, and then I have a plus 39.2 equal to 0. Okay, and I think you probably can tell what I'm going to point out. So you see, this is, there is only one unknown in this, so we can solve it. The unknown is T, however, it's a quadratic equation. And it's not a quadratic equation where we're going to be able to, factorize it, right? So we're going to have to use the quadratic formula. So like T is going to be equal to minus B plus or minus the square root of B squared minus 4AC over 2A, a formula which, by the way, is here, I think, somewhere, that you don't have to remember. And we're just going to have, this will be my A. So my A is equal to 4.9. My B is equal to minus 44.1. My C is equal to 39.2. And so I'm going to sub all of those in here, and I'm going to get t. But the thing about this here, because of that plus and minus, right? That gives me two answers for t. So I'll get a t1 and I'll get a t2. And t1 will be the time when I pass by this 39.2. This might be, this, you've thrown the ball upwards and then like your friend's looking at the window type thing, and your friends see the ball go up and your friends see the ball go down type thing. So this t1 will be the time when it goes past the window, and t2 will be the way back down. Okay, and that's how that will work. Okay.